Welcome back. In the last episode, we explored LLMs, so large language models, the systems that feel so fluent but that don't really understand. We saw that beneath the fluency, they are probability engines predicting one word after another. But what actually makes that possible? What's the architecture underneath it all? Today, we peel back the curtain and explore the foundation of modern AI, which is neural networks. We'll look at the math, the economics, and the deeper human reflections about what it means to learn. So, let's start with something simple, with something human. Results day was just a few weeks ago, and like many families, we had some big discussions. Now, my nephew had to decide whether to go to university, take up a degree apprenticeship, or start work directly. Now, that's not a straightforward yes or no question. There are lots of factors involved: the university's reputation, the location, the exact course on offer, employability prospects, student experience, and even practical things like commuting time or being close to family. And here's the key point: each factor matters differently to each person. So, for one student, reputation carries the most weight. For another, it might be location. And for somebody else, employability prospects. So, how does a student actually decide? Well, the answer is that they do by creating, whether they know it or not, a kind of weighted average decision matrix. So, each factor gets multiplied by how important it is, then you add it all up, and whichever option scores highest becomes the most rational choice. Now, let's take that and zoom that into AI. And that's exactly how an artificial neuron works. So each input, whether it's a pixel in an image, a word in a sentence, or a sound wave, it gets multiplied by a weight, just like each factor in that university decision. Then the neuron sums everything up and passes it through a filter called an activation function, which decides whether the signal should fire forward. Now, on its own, one artificial neuron isn't very powerful, but connect thousands of them, then millions, then billions in structured layers, and something extraordinary happens. So, just like students weighing many factors to make that one decision, the network layers its decisions again and again until patterns emerge that look like recognition, reasoning, and even creativity. Now, let's think about this economically, because in economics, we know that scale matters. So, a single decision maker with a handful of factors can only capture so much complexity, but you scale up and suddenly you get new possibilities opening up. And that's exactly what happened in AI. The early neural networks were small and clunky, but as researchers added more layers, more parameters, more computing power, something fascinating happened: emergence. Abilities appeared that no one explicitly programmed. A network trained to predict words suddenly translated languages. Another trained on images started to recognize objects it had never been explicitly taught. Now, this is what economists would call a non-linear return to scale. You don't just get a bit more performance when you scale up, you sometimes get entirely new capabilities. But scaling is expensive. Training today's largest models can cost tens or even hundreds of millions of dollars. You would need rare chips, huge server farms, mountains of electricity, and oceans of data, and that creates concentration. Now, in theory, the architecture of neural networks is open, so anyone can read about it in a textbook. But in practice, only a handful of companies and governments can afford to train models at this scale. And the result is a paradox: access, which is democratized at the user level, which means that anyone with a phone can tap into ChatGPT or Google Gemini. But the power to build and shape these systems is centralized in just a few hands. And that's not unlike financial markets, because we know that in finance, the models are public knowledge, but only a few institutions can operate at the scale required to dominate. And that centralization creates both efficiency and fragility. So let's take a step back and just reflect on what all of this means for us beyond the math and markets. Let's think about learning itself. So, human growth also happens in layers. Like a child might start with sensations, then learn words, then grammar, then stories, and then wisdom. So each layer builds on the one before. And neural networks do mirror this to an extent, but with a crucial difference. So their layers are mathematical, whereas ours are lived. And that's where values come in. Let's take authors like Daniel Kahneman in Thinking Fast and Slow, reminding us that humans have two systems of thinking. System one is fast, intuitive, pattern driven, much like how a neural network operates. And system two is slow, deliberate, and reflective. And it's that second system that grounds us and it keeps us from mistaking fluency for truth. Or let's take atomic habits, the big idea that small changes, repeated consistently, compound into transformation. Neural networks teach us the same principle. Each small weight adjustment is trivial, but billions of them together create astonishing new ability. But here's the caution. In life, unchecked growth can become dangerous. In biology, growth without regulation becomes cancer. And in society, growth without values can lead to a mess. And in AI, scaling without reflection might create systems that we depend on but don't truly understand. And that's why the metaphor matters. Neural networks aren't just technical systems, they're mirrors. They show us that scale transforms, but they also remind us that growth needs grounding in meaning. So here's where we've arrived. Neural networks are the architecture of learning, layers of weighted decisions that, when scaled, unlock extraordinary power. Economically, they concentrate resources and reshape incentives, and spiritually, they remind us that growth without values is fragile. Now, in the next episode, we'll explore how we actually teach these systems. How do they learn from trial and error? How do we reward or punish them into better performance? That's the world of reinforcement learning, and it takes us closer to understanding how machines, in their own way, practice intelligence. See you in episode 5.